Okay, so now what we're going to take a look at is how the pH of a weak acid solution changes as a function of the relative amounts of weak acid and conjugate base. So we've already showed through the Henderson-Hasselbalch equation that the amounts of weak acid and conjugate base directly affect the pH of the solution. So the reaction we're going to be doing this for is looking at our weak acid, and we're just going to keep adding amounts of OH minus because we know that OH minus, that hydroxide, will accept the proton from the acid to generate the conjugate base and water. So we want to see, as we react more HA and abstract those protons to generate more A minus, thereby changing the relative amounts of these two, how the pH is going to change. And we're going to show that graphically using a titration curve. Okay, so the titration curve is going to have pH on the y-axis and the amount of OH minus that we've added along the x-axis. And graphically, that's going to look like this. Okay, so we know that starting down here at the lowest pH that we have, right down here, that all of our molecules are going to have their proton on them. None of them have reacted with any OH minus, so everything we have is in the form of weak acid. Then, as we start moving along our titration curve, and we start adding hydroxide ion, we know that some of our weak acid is being converted to conjugate base because it's undergoing reaction. But for the most part, at this point, the amount of weak acid that we have is greater than the amount of A minus. So we have more weak acid than conjugate base. But eventually, when we're halfway through that titration, we will have reached a midpoint, and at that point, we will have reacted half of our weak acid molecules. So that means at this point right here now, actually maybe I should change that to a gold color, the amount of HA, oops, I forgot to put the H. The amount of HA that we have is equal to the amount of A minus. And we also know from looking at our Henderson-Hasselbalch equation that at that point the pH value is equal to whatever the pKa is for that particular weak acid. So now, as we continue to add more hydroxide ion, we keep reacting that HA to yield even more A minus. And since we've passed the 50-50 mark where we have an equal distribution of conjugate base and weak acid, we now have a situation where there's more conjugate base than there is weak acid. And then eventually we will reach a point. Oh, I'm all out of colors. Oh, no, I'm not. Cool. I just found a little color button on here. We will reach a point in our titration where we've now reacted all of the weak acid and it's all been converted into A minus. And we know that that's called the endpoint of our titration. So what's really cool about this titration is we see this region here in the middle, ooh, purple, where even as we keep adding hydroxide ion as we move along here, the slope of this graph is pretty flat. So we don't have a change in pH even though we keep adding more and more hydroxide ion. So what we call this region, right through here, this is our buffer zone. So remember, a buffer is going to be a solution that has both weak acid and conjugate base, and it is able to resist a change in pH, even as you add hydroxide, or we could also just as easily been going from right to left and adding acid to our solution. And if we were doing that, we would still be resisting a change in pH. So buffers can resist changes in pH even when you add acid or base. And the rule of thumb for how long this pH remains constant, so like what the range is that you have a buffer zone for pH when your pH, or excuse me, your pKa is within 1 unit of the pH that you want. So for example, if you want to have a buffer at a pH of 4.5, then the pH of your acid, the weak acid that you're going to use to make that particular buffer, needs to be between 3.5 and 5.5. So you're within 1 pH unit of the region where you want to buffer. And we'll go over that more later. But one thing that's really big in biochemistry is we want to say, we know the pH of this solution. We need to know if this particular organic chemistry functional group is protonated or not, because that's going to play a role in the structure of our larger biomolecules. So we need a quick rule of thumb so that we can figure out really quickly whether or not most of the molecules are protonated or whether they've lost their proton. So the shortcut looks like this. If the pH of your solution is less than the pKa value, then the proton is on the acid still. Or I should say most of the acids still have a proton. Whereas if the pH of your solution is greater than the pKa of the acid, then most of your acid molecules have dissociated and the proton has been removed. So let's just look real quick at an example of that. So a good example would be looking at acetic acid. So acetic acid looks like this. And we know that it dissociates to form acetate ion and H+. And the pKa of this particular proton is 4.76. So that means that if your pH is less than 4.76, you primarily have most of your molecules in this form. The proton is on. However, if your pH is greater than 4.76, most of your molecules, greater than 50%, have deprotonated to form this particular species, the conjugate base. We could also look at that using our titration curve. So if I drew a titration curve for the deprotonation of acetic acid, it would look like this. So here's pH, here's the amount of OH minus that we've added. So right here, we said the pH is equal to the pKa. And so at this point, we're at 4.76. So we've already said in our last graph, our last titration curve that we made, that if our pH is below 4.76, we are down on this point of the curve, which means most of the molecules are in the form of the weak acid, which is acetic acid. But if we are above a pH of 4.76, we're up here on the graph somewhere, and we know that most of the molecules are now in the form of the conjugate base. And of course, then you have the two endpoints. So you have where you started, where you had all acetic acid, and then you have, of course, where you end, and you have all acetate. So in your textbook, some good figures to review different titration curves are figures 217 and 218. They have lots of examples for different titration curves of various weak acids. So the next question we want to ask is, why is it in this buffering range where you have this flat region, why is it so hard to change the pH? How is the weak acid and the conjugate base, how are they working together to resist that change in pH? So it turns out that we have to look at the chemistry that those individual ions are undergoing. So it turns out if you add acid to a buffered system, so we're adding H+, which we know is really a hydronium ion, that acid will react with the conjugate base form of the buffer molecule, and it will get used up, and it will form water and weak acid. So basically we're adding H+, but it's not staying free. It's reacting to form water and weak acid, so there's no net change in pH. At the same time, if you add base to your buffer system, it instead will react with the weak acid of your buffer, so the weak acid form of your buffer molecule, to form water and conjugate base. So again, no net change to the overall concentration of H plus in your solution. So that's why your buffer is able to resist the changes in pH. The added acid to your buffer or the added base react with either the weak acid or the conjugate base from your buffer molecule so that there's no change in how much H plus is floating around, so there's no change in the overall pH. So you can imagine this is going to work best when you have equal amounts of conjugate base and weak acid. So if we go back to our titration curve, we know that you are the flattest in this titration curve, right in that midpoint, and we know that's the 50-50 distribution of weak acid and conjugate base. So at that point you can react really well to prevent changes in pH in either direction, adding acid or base. So the best buffers are close in pH to the pKa of the weak acid. So that's where we said that the pH that you're buffering at is within 1 unit of the pKa. And we also want to have as close to equal concentrations of weak acid and conjugate base. If you only have one or the other, which means you were only down here or you were only up here, any added amount of acid or base is going to result in significant changes then in the pH. You get a really steep slope. Okay, so you want to have as equal amounts as possible so that you're in this range of your titration curve.